management workstream, and today I'm going to talk about cost optimization and management of your Kubernetes footprint. So to set the context, I want to introduce a customer called Contoso, a fictitious character who's running an e-commerce platform with several multi-tier applications. They previously were all on-prem, but they've transitioned to IaaS recently due to recent business growth and increasing resource demands, so they need to keep up. And eventually, they want to migrate all their workloads and all their environments onto AKS for a number of reasons. So scale, automation, high availability, disaster recovery, and cost are some of their top-of-mind challenges and concerns at the moment. So when we look at Contoso's workloads, we notice the following. They have over 10 critical dev, test, production workloads. They're using VMs currently in IaaS as a means for physical and logical isolation, and they've provisioned about 150 DS3 VMs, DS3 V2 VMs, which is costing them over $1,000 per day in this IaaS configuration. And the reason why they've configured so many VMs is multiple VMs per application, per web storage processing tiers in their application environments. So they want to ensure they have enough so that they're scalable, they're resilient, fault tolerant, and to make sure all of those concerns that they had are addressed. Their applications are n-tiered and non-uniform, so different applications might have 3 tiers, some might have 11 tiers. They don't all look alike. And services are also written in a variety of languages. This is an example of what an application in Contoso's IaaS configuration might look like. The key takeaway here is that there are 3 tiers, and each of these tiers are running across a set of fully isolated VMs. So they're completely isolated from each other, and Contoso doesn't want to mix workloads. They don't want to have dependency mismatches. But in practice, with this configuration, having this isolation of environments, having so many VMs, ends up running at a really low utilization. So there's actually a lot of idle resources, wasted resources in these VMs, which causes overspending, over-provisioning, et cetera. But when we adopt a microservice approach and containerize, there are many inherent benefits that we automatically get when it comes to cost savings. So for Kubernetes, you probably all know many benefits such as elasticity, scalability, automation, and importantly, the ability to bin pack and share resources across your workloads. By bin packing, you're able to immediately reduce your infrastructure costs because you don't need to provision as many nodes. And on top of this, Contoso is interested in AKS as their managed Kubernetes platform provider. They like that the managed service will help them spend less time on infrastructure maintenance and configuration, so their developers can spend more time on doing what's important, building the software that is actually empowering their customers. They also like that control plane is free of charge and that they only have to pay for what they actually use. So overall, there's a lower operational overhead with AKS. Some of Contoso's concerns at the moment are, where do I start? What's my infrastructure spend? Am I right size? How do I scale? And how much is saved by migrating to AKS and optimizing my AKS workloads from IaaS and from previously on-prem? All right, so before doing any cost optimization, we need to understand where exactly our costs are coming from. With multi-tenant shared resource environments, we're able to bin pack and get high utilization out of our infrastructure, but this also means that our infrastructure bills are common and all the apps that were previously isolated are now in shared environments. So it's really hard to know, this application is costing this much, this workload is using this much CPU, memory, et cetera. So monitoring and visibility are non-negotiables. They will help us understand where our costs are coming from, track it over the long term, and identify opportunities to optimize for cost. So in comes to the picture, open costs for AKS cost visibility. OpenCost, if you don't know, is an open source vendor-neutral CNCF sandbox project. It was recently adopted and accepted into the FinOps organization, and the code was originally provided by KubeCost. OpenCost provides a great ability to break down cluster infrastructure costs by Kubernetes constructs, so your namespaces, controllers, services, pods, containers, labels, all your standard Kubernetes constructs, and you can get really, really granular with what costs are coming from where. So if there's a namespace that looks really high in costs over the long term, you might be flagged and dig into deeper, looking into why that is, if it's anomalous or not. And we're also excited to announce that Microsoft Azure has joined OpenCost project as a contributing member. So we've already made several contributions to the project to enable a new level of cost transparency for AKS customers and for folks using OpenCost. First, we've enabled customer-specific Azure resource pricing. So we've integrated with the Azure Consumption API, price sheet API, and this pulls more accurate cost and billing details into OpenCost's cost allocation engine. That means your consumption, savings plans, reservadances, any Azure discounts that you use is accurately reflected in this cost allocation breakdown that OpenCost provides you. We've also enabled a CSV cost export functionality, so you can port your cost allocation data into Azure storage, other cloud provider storage, or even local storage for long-term historical analysis. And you can pipe that into any existing data pipelines that your team might have in place today. And we've also enhanced documentation specifically for the Azure OpenCost integrations. And there's a special KubeCon EU build that was released recently. So if you're interested, you could go ahead, try these new features, see what other contributions community members have made to the OpenCost project, and try it out. And all of these features in the KubeCon build will be GA'd May 2nd, so coming up pretty soon. Now I'll do a quick demo of, I'll do a quick demo on how to install OpenCost and configure it with the customer-specific prices and the CSV export to an Azure storage account. All right, we have that running. So I want to install Prometheus because OpenCost is layered on top of Prometheus as their utilization collection agent. You can bring your own Prometheus. You can install Prometheus just for OpenCost. Either way works. And then I will apply the OpenCost YAML deployment. So now we have OpenCost running, the OpenCost pod running. Then I will create an OpenCost role definition and create a custom role. So here's our role definition, basically setting permissions. We've created our role assignments. And it looks like I already have one. That's okay. I'll just use the one I previously created. Then I'm going to create a service principal and grant various permissions so I can actually pull my billing data from my subscription. Next, I need to get billing account info, so our ID and our billing account name. This is required for configuration purposes and when you run the configuration script. Then I will set some environment variables and run the billing rule bash script. Then we go back to the OpenCost YAML, and you can see there's a special KubeCon EU build image right there. That's the one that you can use to test out if you're interested. And we'll also set the Azure billing account, and Azure offer ID environment variables in this OpenCost deployment file. And just like that, we apply the changes, and we will have that customer-specific pricing rolling into the OpenCost data that is available to you. For the next part, the CSV export to Azure Storage, first we'll go into Portal and create a new storage account, because we'll be using blob storage for this purpose. So I will just do that in Portal. We name our storage account. And as it deploys, our next step will be to create a container within that storage account. So this is where your exported data will be pushed to at the end of each day after it's been configured. Naming convention, you could use whatever you want, whatever works for your team. And the only important step, depending on whatever you name it, is we need this URL. So the path to your Azure Storage container, we will grab that. We'll go back to our OpenCost YAML, specify the export CSV file path. And one other small note, we will add the file name. So you could call it whatever you want again. The first time you configure OpenCost, it'll automatically create this file and push it into your container. Every subsequent day that this runs, that file in your container will automatically be updated and new data will be appended. Last couple steps, we'll create a service principal. So we have write access to the blob storage container. And here we will create a secret with our service principal app ID, tenant, and password information in our OpenCost YAML. You can set those as these environment variables, and then we will apply the changes once more. And then after a few days, you'll see it takes about 1 to 2 days after your first configuration for the data to start propagating into your container. Once you see this in Portal, you can download it. You can create an event hub to push it into Power BI or Synapse, Line Analytics, whatever other tooling you are using for any existing data analysis. And let's look at the schema a little bit, what kind of data is provided in this CSV file. So it's a little bit small, but key Kubernetes constructs that we have: namespaces, controller kinds, controller name, containers, labels, and we also have utilization metrics. So your CPU utilization and request, your RAM, networking information, GPU, persistent volumes. And then we have our Azure asset breakdown. So how much is total cost of CPU, total RAM cost, total network cost, those kind of details. So this is a new level of granularity of cost allocation data that can enable your teams to do chargebacks, just have a better grasp of where costs are coming from, and again, identify opportunities to optimize your cost. And here's an example of what you could do with the CSV export. So as I mentioned, I just set up an event hub and pulled this data from the storage account into Power BI. And I've separated the data by namespace because that's commonly a way that customers will isolate workloads, separate workloads by teams, et cetera. So that's one example of what you can do. I'm looking at requested versus used CPU to see if maybe there's better ways I can set my requests and limits to optimize and bin pack better. And also looking at CPU idle percentages as a quick calculation to see if there are resources that are just sitting there and that can be optimized better. You can also use OpenCost in Cluster UI for real-time, quick data visualizations. Again, they have the same breakdowns and ways of pivoting, so namespace, controllers, services, etc. And this is a real-time, quick snapshot. So a little bit tougher to look at the long-term trends, but for a quick glance, if you want to validate something or validate an application, look at its spending, this is a great way to do that. Okay, so Azure Monitor. In addition to cost visibility, monitoring utilization can also help Contoso preemptively identify high spend areas and areas they need to look into deeper. You can use Azure Monitor to optimize data ingestion by specifying data collection frequencies. You can limit ingestion to specific namespaces of interest or concern. You can also optimize costs with Prometheus metrics collection. So this is the Azure Monitor Managed Prometheus. The managed offering is fully managed collection, storage, querying, and evaluation of the data. It's highly available and scalable. You can monitor cluster autoscalers and have great long-term retention of your data. As you monitor, there's also going to be a lot of data and logs that are becoming available. So storage, processing, querying of this data can be very expensive. But Azure Monitor also offers low-cost alternatives to these verbose logs. Container Insights offers a schema for container logs called Container Log v2. And Azure Monitor is also working on a number of things. For example, enabling enhanced settings to collect only specific data that's needed, as well as smart defaults. So automatically select monitoring of and settings curated to your AKS cluster's configuration. So let's revisit Contoso's compute bill. Before we had that IaaS baseline of 150 VMs. Now with monitoring and visibility in place, we have a new baseline for their AKS costs. Immediately, we see this big drop down in terms of cost per day, as well as the number of VMs. Just because inherently with AKS, we can bin pack better, meaning we don't need as many VMs to be provisioned. Some fundamental optimization techniques now. First, portal presets. So the view you see here is actually not in production right now. It will be in a week's time or two, really shortly after KubeCon. But we have some changes to the presets that you'll see above. It can be really difficult when you're configuring your clusters to choose the right VM instance, region, number of nodes, availability zones, etc. So these portal presets are a really great way to offload that initial challenge, especially when you're trying to strike a balance between cost and then also your resource requirements. Some best practices for dev and test clusters. So small dev test clusters, when they're left unattended, they can also generate and spin up a lot of costs. You can turn off clusters that you don't need running 24/7, so those small test clusters running only Monday through Friday. You don't need it on Saturday, Sunday. You can use cluster start-stop. Doing so will shut down all your system and user node pools, but your objects and cluster state will all be maintained when you restart. You can also take note of free versus standard tier. So free tier is common for small clusters as well. It's a great cost-saving option for those small cluster scenarios, but when you're moving to production and you want better uptime availability for your control plane, that's when we really encourage you to upgrade to that standard tier. You can also use spot nodes, spot node pools. So spot VMs allow you to consume unutilized resources at a significantly discounted price. About 90%, I think, as when compared to pay-as-you-go prices. That's a very significant amount. Spot VMs are best for workloads that have interruptions, batch processing jobs, testing environments, things like that. And VM SKUs and sizing. So very hard, as I mentioned, to initially anticipate what kind of VM SKU might be best for your workload. That's okay, because Azure and AKS support a really wide variety of compute options. We have memory, CPU, network-specific and optimized virtual machines, as well as GPU-optimized machines. So if you have memory-bound or compute-bound workloads, you can choose SKUs that are more aligned with what your resources need and demand. Azure also supports ARM64-based VMs. These are excellent for running scale-out workloads, for web servers, open source databases, because you really get a great performance for a lower cost. So another great option to look into. And we also have auto-scaling techniques. So auto-scaling is great for meeting demand and increasing availability. For application and pod scaling, these auto-scalers can help you save costs by dynamically provisioning and shutting down underlying infra as needed to meet the required demands of your workloads. We have a couple scalers to call out. So vertical pod autoscaler is our first one. This is a great feature tool to help you dynamically set your requests and limits. You also can get recommendations for how to set those requests and limits. When you set requests and limits by yourself, it's typically challenging to guesstimate how to accurately do that, but it's really important for efficient workloads. You can also use Cicada, which a couple of the PMs in previous sessions called out and Ali demoed before. This you can scale on a number of events, HTTP requests, based on compute, based on memory, and there are over 50 plus scalars that are represented that Cicada can scale on. And for horizontal pod autoscaler, you can monitor and autoscale the number of replicas based on your Kubernetes metrics. So as you see demand increase, you'll also see your number of replicas increase, and likewise, as memory and CPU requirements decrease, your replica count will decrease as well. For node autoscaling, this is also a great option to dial back or dial up the number of VMs that you need to provision at any time. Manual scaling is a great option if you have anticipated application load or deployments, but cluster autoscaler is an even better option for taking away that manual element and automatically responding to unscheduled pending pods and load, and automatically scaling up or down the nodes in response. We also have scale down mode. In this case, rather than deleting nodes, the nodes are deallocated. So in a deallocated state, you won't need to pay for compute resources. You will have to pay for OS or any data storage disks attached. But it's a great option for if you need to scale back up really rapidly and you don't want to shut down all of your nodes. And now we have our second demo. Let's see if this works. All right, so first, we have our cluster. This is going to be a demo of cluster autoscaler, VPA, and Cicada scalers. So we're going to set up a cluster with scale down mode, deallocated, enabled. As it's provisioning, we will see the following. And here we've also enabled cluster autoscaler. We've set a minimum count and a maximum count of nodes so the node pool can be scaled up and down. And the node pool is being deployed. All right, and then we're going to use Kata to automatically scale our application workload. Here, you'll see we have a deployment. In this workload, there is basically an analytics workload that listens to messages from a service bus queue. So whenever we push load onto the service bus queue and consume it and analyze it, Kata will scale our nodes based on how much resources is needed. So this is our service bus queue. For Kata, oops, let me pause. For Kata, we'll set the definition of the scaled object, and this will take parameters from the pod spec and listen to the queue. And for example, if we have a queue depth that's more than 10 and we need to start scaling up, Kata will automatically kick in and help us do that. Here you can see I've set the replicas of the deployment to 0 because we want Kata to automatically increase our replica count and see that change as the load starts coming in. And this is what the load might look like. Here we see, oh, we skipped, but that was a managed Grafana dashboard that we'll refer back to. So we're checking our pods. We don't have any pods at the moment since we set our replica to 0. And we check our nodes as well. You can see there's a lot of not ready states. But as soon as we push some load onto the server, about 2,000 messages to the server, we'll see things changing up quite a bit and pretty quickly. See our messages coming in. And let's go back to our Grafana dashboard and monitor the changes. Before that, we can see all of our pods. Now a lot of pods have been created, all in pending state, but they're quickly being provisioned and spun up. Same with our first set of nodes, our pods are running now, as well as our first set of nodes. A lot of them are now in the ready state. And there we go. Most of our VMs are ready to go. And you'll see now memory and CPU on the left-hand side, they're changing in real time. CPU is going way up because of all our pods and all of their requests and the resource requests. Just changing the view in a percentage so we can see those changes. And for memory, we actually, interesting, we see that dropping because we went from having no nodes to having many, many nodes. So Grafana is basically reprocessing and reseeing what our baseline is for memory. Another call out here is notice how low our memory and CPU utilization rates are. They're mid-20s. That is very, very low. So in this scenario, we can BIM pack better to maximize our utilization. Hopefully, we could see those numbers in the 80s to 90% ranges for a fully utilized node. And this takes a while. Let me see if I can fast forward here. Might have actually lost our spot in the demo, but that's okay. Since I can't pull that back up, I'll just talk about VPA as well. So when you enable VPA, you can get automated or you can get recommendations for what you should set your requests and limits. In the demo video, I had set it to automatically change and look at my historical usage of pods and adapt what my resource and requests are. But in practice, would highly recommend looking at the recommendations and making those changes yourself, just so you know what exactly is happening with your workload. And yeah, it can result in some problems in production if you have it automatic, and you don't want that to happen, so definitely look at the recommendations. Going back to Contoso's compute bill. So we're seeing that daily cost number tick down gradually. We've enabled our autoscalers, cluster autoscaler, VPA, and CADA, and we see a huge savings, over $500. These autoscalers are fairly simple to implement, but their benefits and the cost benefits of configuring them are pretty outstanding. How can we take this one step further now? How can we become even more cost optimized? One other option is to leverage Azure discounts. So Azure offers a number of discounts, reserved instances, and Azure savings plans. In these discounts, you make an upfront commitment to compute resources, and you pay it at a highly reduced cost. So these are terms that are fixed over 1 to 3 year period. Reserved instances are a little more strict in the sense that you have to specify a SKU family and a region that you're committing to. But the value is you get up to 72% saving compared to pay as you go. For Azure Savings Plan, you have a little more flexibility. You're not limited to a SKU or a region. You just specify an hourly commitment, a dollar value that you want to spend, and that'll apply to your resources across the board. It'll apply, they can be in different resource groups, they can be across your whole Azure account, and it'll still apply. And if you go over your initially committed resource value, you just continue to pay at a pay-as-you-go rate. And lastly, we have the idea of FinOps and a cost savings culture. So FinOps is about adopting cost-saving culture. It's more of a philosophical and organizational method to drive deeper cost savings. It's about collaborating across teams, collaborating with finance, engineering, technology, business teams, aligning everybody so there's more transparency into cloud costs, there's more accountability of respective teams and how much spend and how much costs they are generating. And it also helps when you have this new transparency to drive accountability and promote cost-conscious decision-making. So in summary, did we address all of Contoso's concerns? Where do I start? We chatted about fundamentals, best practices with the portal presets, the dev test clusters, and picking VM SKU types. What is my infrastructure spend? We talked about monitoring and visibility and how those are non-negotiables, how they can give you better cost transparency and insight into where and what to optimize. Am I right-sized? We looked at the pod autoscaler, setting those requests and limits. First, when do I scale? We looked at using cluster autoscaler so you can automate that and scale dynamically based on resource demands. And there are 2 questions that are outstanding. So how much is saved by migrating to AKS, and how much is saved by optimizing my AKS workloads? Let's take a look at this slide one last time. We keep adding line items to the bottom of it and see that cost keep ticking down. So this is the main punchline of this session. First, there's immediate cost savings that are out of box when you lift and shift from IaaS to AKS. Second, monitoring and visibility. Again, they're non-negotiables. Open cost gives us a really good indication of what costs to dig into, and deeper visibility, granularity into cluster costs. Third, working with autoscalers makes us, helps us bin pack better and share and spread our resources across a shared set of resources and dynamically adjust based on demand, workload demand. And 4, we know the value of Azure discounts to reserved instances and saving plans. Yes, they're a long-term commitment, 1 to 3 years, but they really have ticked down our costs here. Just by using reserved instances, we've dropped from triple-digit dollar per day to double-digit dollar per day. So implementing a few cost optimization techniques and tools can go a long, long way in your cost optimization journey. And of course, these numbers that you see here will depend on your environment and your specific workloads. But in Contoso's case, which we've seen as a realistic scenario, can have undeniable cost savings. So this is the last thing I want to leave you with. These numbers are huge numbers when it comes to cost savings. But just by working through a small subset of tools and techniques, Contoso had a 94% reduction in their AKS baseline cost and a 96% reduction from their initial IaaS costs. So investing, continuing to revisit, monitoring, and being intentional with your cost optimization can save you and your organizations a lot in the long run. Yeah, cost optimization shouldn't be an afterthought. It should be rather considered as an opportunity for improvement. And with that, yeah, thank you so much. I hope you're able to walk away from this presentation with new tips and tools. Thanks.